Let me start the recording. Okay. Usually I don't present the invited people, but this time maybe since there are a lot of new people coming, I'm going to say just a few words. Jan Bricmont is an expert in philosophy in quantum foundations. I think he's both a philosopher. He would define himself as both philosopher and physics. Of course, more physicists than philosophers, but also philosopher. And he recently wrote a book, I think 2017, on quantum sense and nonsense. And today he's going to give a talk on Schrödinger's paradox and proof of non-locality using only perfect correlation. Thank you, Jan. You can go ahead.
Okay, thank you, Christian, and hello, everybody. So the work here is done in part by Douglas Hemmick, who doesn't have an academic position, so he has no academic address, but he used to be a student of Shelley Goldstein, and the paper is mostly due to their work, and why I'm here, it's a somewhat accidental reason. But anyway, so I'm going to... So the goal of the talk is to give a proof of non-locality, which is using perfect correlation between measurements and an idea of Schrödinger. And I will also illustrate how non-locality manifests itself in the Broglie-Bohm theory in Bohmian mechanics. The proof is not going to use any Bell-type inequality, and essentially doesn't need to be experimentally checked if you believe some basic statements about quantum mechanics. So in 1935, there were three important papers on foundation of quantum mechanics. One you all know is Einstein-Podolsky-Rosen, the EPR paper. You also all know probably the Bohr response to it, or I put response quotation mark because I think I missed the point, but anyway. And then there's a paper by Schrödinger, the present situation quantum mechanics, which is sometimes called the cat paper because that's the paper where he mentions the cat which is both dead and alive. But it also contains extension of the EPR argument that we will use. And it's, I think, the proof that I'm going to present, as I say, you know, my role is minimal, so I can say good things about it. I think it's very neat and very clean and conceptually clear. And of course, it's based on an argument of Schrödinger. And if only from a historical point of view, it's worth noticing that Schrödinger perfectly understood Einstein, Podolsky, and Rosen, unlike Bohr. The history of physics is that Bohr answered adequately to EPR, and Schrödinger is basically ignored except for the cat argument. Anyway, so almost 30 years later, in '64, Bell based himself on the EPR paper to prove that there are non-local causal effects in nature. His proof used some inequalities that had to be verified by aspect and other, and Bell's proof is often viewed as a no hidden variable theorem. Bell, in another paper, and Cocken and Specker did prove what are called no hidden variable theorems, but it's not the same paper exactly. But there's a lot of confusion about what no hidden variable theorems really mean, as well as what Bell really proved. Here we combine Schrödinger's generalization of the EPR argument with some no hidden variable theorems in order to prove the existence of non-local effect in nature without using any inequalities. So enough announcement. Let me go to the EPR argument, which is given in a version due to David Bohm. And I first consider an experimental situation that may at first sight seems baffling. One measures in a given direction the spin of a particle that is prepared in such a way that according to quantum mechanics, the result will be random with both outcomes up and down equally probable, which means that you take this many particles in the same state, you repeat the experiment many times, and the statistics is more or less half up and half down, okay? Yet there is somebody called him Bob who claims to be clairvoyant and does predict at each run of the experiment and with 100% success what the result will be. How does Bob do it? Well, there is a trick. He has an accomplice, Alice, and there is a box between Bob and Alice that sends to each of them one particle belonging to an entangled pair, which means that their joint quantum state is of the form A up, B down, minus A down, B up, where the left factor refers to the particle sent to Alice and the right one to sent to Bob. That state, according to ordinary quantum mechanics, means that the spin measured by Bob will have equal probability to be up or down, but is perfectly anti-correlated with the one of Alice. So the trick is simply that Alice measures the spin of her particle first and sends to Bob a message giving a result. then Bob can with certainty predict what the result of the spin measurement on his side will be, namely the opposite of the one of Alice. So there is no mystery here, of course, and within ordinary quantum mechanics, this is explained by the collapse rule. When Alice measures the spin of her particle, the state psi collapses to A up, B down if Alice sees the spin up, and to A down, B up if she sees the spin down. So this superposition here is reduced to one of these two terms if Alice makes an experiment. After the collapse, the spin of the particles on Bob's side is no longer undetermined. It is with probability 1 up if the collapse state is A down, B up, and down if the collapse state is B down, A up, B down. So what does this collapse mean? Is it a physical operation, i.e. does the measurement by Alice change the physical situation on Bob's side, or does it have to do only with information? Meaning that through the measurement of Alice, we simply learn something about the physical situation on Bob's side. So this is a question. What do you, is there something physical going on when you do a measurement on Alice's side, or you just learn something on Bob's side that pre-existed to either measurement? It is important for the rest of the discussion to keep that dilemma, which we'll call the EPR dilemma, in mind. And if one chooses one horn of that dilemma, to stick to it and to its meaning. A lot of confusion comes from the fact that some people jump from one horn of the dilemma to the other in the course of a discussion. So consider the first horn. What could the physical operation be? You may think that before Alice's measurement, the spin of the particle on Bob's side is genuinely undetermined or non-existent. There is no fact of the matter as to what the value of the particle, the value of the spin is on the other side, and that it acquires a given value only after Alice's measurement. But that means that some sort of non-local action or action at a distance took place. Alice's measurement creates the value of the spin on Bob's side, value that didn't exist before that measurement. Consider the second horn. The spin of Bob's side was determined before Alice's measurement, and we simply learn its value by doing that measurement. But that also means that the quantum mechanics is incomplete in the sense that EPR gave to that term. There are facts of the matter about the spin of the particle on Bob's side, it's either up or down, that are not described by the superposed state here, because the superposed state here does not save the spin of the B particle, or for that matter of the A particle, is either up or down. I mean, it just doesn't include the value of that variable. It just says that statistically you will have 1/2, 1/2. Okay, but for a particular experiment, it doesn't give you a value of the spin. Now, let's go to Schrödinger's generalization of the EPR argument. First, you define, well, we work with finite dimensional Hilbert spaces or vector spaces, and you take a product, a tensor product of two such spaces, and you define a vector there to be maximally entangled if it is of the following form: a sum of tensor product of basis vector phi n and psi n at our orthonormal basis in that space. And it's normalized like that, so that the sum of the square of the coefficient is 1, because the n terms and the square here is 1/n. Since we are interested in quantum mechanics, we refer to those vectors as maximally entangled states. And by convention, we associate to each space in the product a physical system. Namely, we consider phi n as a basis of state for physical system 1 associated to Bob, and psi n basis of state for physical system 2 associated to Alice. I mean, this is just terminology, okay? It turns out that the above representation is valid in any basis. Namely, if you change the basis phi n to phi n prime, then there's a well-defined way, which I will not explain, to find another basis psi n prime, so that psi keeps that form. A simple example of a maximally entangled state was the one I gave previously. The psi here, which you can rewrite as a tensor product, just the product of these vectors, psi n times phi n, with the following choice of phi 1, phi 2, psi 1, psi 2. Okay. Now I'm going to use two mathematical facts in the talk. The first mathematical fact, and that was Schrödinger's remark, is that you can associate to each operator of the form 1 times O, O being an operator, meaning that it acts non-trivially only on particle 1 on Bob's side, an operator of the form O tilde times 1, meaning it acts only on particle 2, where 1 denotes the identity operator, and that's why I say it only acts non-trivially on one side. Now, in the slides, which I will leave you, and in the paper, I describe how to construct O tilde given O and given the maximally entangled state, okay? But that's not, you know, that's not the point. That's not the point of the, I mean, I'm not going to give the proof here of that. The operator O tilde has the important property that if I n eigenstate of O with eigenvalues lambda n, then the state psi n eigenstate of O tilde also with eigenvalues lambda n. Here is a simple example of operator O tilde with that state. Well, again, I identify phi1, phi2, psi1, psi2, and if O is that operator, which has eigenvalue phi1 with eigenvalue -1 and phi2 with eigenvalue 1, then if you go to the procedure to construct O tilde is simply -O, and then O tilde, saying that O tilde has the same eigenvalues as O, and eigenvectors, I mean, corresponding eigenvector, translating the perfect anti-correlation for the spin measurement, because we had anti-correlation, and here the operators are perfectly correlated, but one is just minus the other, okay? Anyway, that's just an example, but let us now generalize the EPR argument by applying the result of the previous subsection to spatially separated physical system. Suppose you have a pair of physical systems whose states belong to the same finite dimensional Hilbert space, and suppose the quantum state is a maximally entangled one. So I'm just repeating that. Then any observable is represented by a self-adjoint operator O, which has therefore a basis of eigenvector. And since the representation of the state is valid in a basis, you may choose the set phi n as the eigenstate of O and let lambda n be the corresponding eigenvalue. Okay, then I'm copying the state. If you measure that observable O, the result will be one of the eigenvalue, each having probability 1 over n, since the probabilities are given by the square of the coefficient, and each coefficient is 1 over square root of n. If the result is, say, lambda L, the collapse state of the system after the measurement will be psi L times phi L. Then the measurement observer O tilde on system 2 will necessarily yield the value lambda L. This is just repeating in more general terms what I just said about the simple example with n equal 2 before with the state I started with. Reciprocally, if you measure an observable O tilde on system 2 and the result is lambda k, the collapse state will be psi k times phi k, and the measurement observable 1 on system 1 will necessarily yield the value lambda k. So I'm summarizing what we just said. It's called the principle of perfect correlation. If you have a maximally entangled quantum state, for each operator on system 1, there is an operator O tilde acting on system 2, such that if you measure the physical quantity represented by O tilde on system 2, the result is value lambda k, then measuring the physical quantity represented by O will yield with certainty the same eigenvalue lambda k, and of course vice versa. Now, the following property will be crucial in the rest of the argument, and that's what I want to prove is not true, is the property of locality. Locality says that if the system 1 and 2 are spatially separated from one another, from each other, then measuring an observable on system 1 cannot possibly, has no instantaneous effect whatsoever on system 2, and measuring an observable on system 2 has no instantaneous effect on system 1. I have a problem with that. So what should I do there? I mean, okay. We must also define a non-contextual non-contextual value map means. So again, H is a finite dimensional Hilbert space, and A is the set of Hertz-adjoint operators, so they are the set of quantum observable. And suppose there are situations in which, like the spin in the EPR situation, which I discussed before, the observable for which the result of measuring AO is determined already before the measurement. Okay? Suppose that O has in this situation a pre-existing value which is revealed by the measurement, you learn what it is, and not merely created by the measurement. Of course, this implies that for every experiment measuring O, the result of that experiment situation must be V of O. It's a real value which you discover by measuring. There are different ways to measure the same observable, we'll see that later. And in that situation, and assume also that the situation is such that you have a pre-existing value V of O for every observable in our algebra of operator. Then we would have what we call a non-contextual value map, namely a map that assigns a value to any experiment associated with what is called in quantum mechanics a measurement of the observable O. There are different ways to measure the same observable, as I just said, and an example will be given below. The value map is called non-contextual because it associated with the same quantum observable, we obtain the same value. I mean, saying it's non-contextual is first really saying that it's a real value map, because if you find the value of the operator O, which pre-exists for that particular particle to the measurement, then of course it's a real value. And contextual, there wouldn't be a real value. It would depend on the way you measure O, and that's exactly meaning that it's not, you don't discover a real property of the particle. Now comes the Schrödinger's theorem. That's the observation of Schrödinger. The perfect correlation plus locality imply the existence of a non-contextual value map. If I were to measure O tilde, if we were to measure O tilde and obtain the result lambda k, we would know that the value of O is lambda k equal lambda k is the result that would one obtain if I measures O. Now comes the crucial point, the reasoning. By the assumption of locality, the measurement of O tilde, since it's associated to the second system, could not have any effect on the first system, and thus this value V of O has to pre-exist to the measurement of O tilde, and this would not depend upon whether O tilde had been measured or not. Because I know that if I measure O tilde, then I will get a certain result, and therefore that result must be also the value of the operator O when I do no measurement whatsoever. But even if I don't do a measurement of O tilde, that's true, because so I prove that there exists a pre-existing value by this reasoning without actually doing any measurement on O tilde.
Sorry, Jean, I think there's a question, unless he misclicked, from Jeremy.
Yeah.
So, hi, thanks. So I just wanted to ask if you could say a little bit more about why that follows from the assumption of locality. This non-contextual value map.
Because locality says that when I do a measurement on one side, it has no effect whatsoever on the other side, right?
Mm-hmm.
Now, if you measure omega tilde, O tilde, and you obtain a result, let's say lambda k, then do you agree that that means the value on the other side is lambda k?
I mean, certainly it implies certain facts about, I mean, if we're looking at the operational level about what your observer who sees lambda k on the one side will see when they talk about the result for Bob who gets lambda k on the other side. Yeah. But how is this not just begging the question, for example, against many worlds view?
Okay. Okay, the many worlds view. Can we stick to one world for a minute? I mean, I don't agree that there is the many worlds avoid this problem, but that's a longer, more complicated discussion. So if we agree that there is only one world, do you agree that the result would be, I mean, even in every possible many worlds, the result would be perfectly correlated. So I don't see why it avoids that. But let's assume only one world for the moment, okay? Then do you agree with the reasoning or not?
Even if we assume only one world, I'm not sure that we're not begging the question against alternative ontologies. Like, for example, I don't know, a participatory realist view, like a cubist view, or a state relative view.
I don't know what that means. Cubists, as far as I know, are simply a different philosophy. They just don't want to answer that question. I mean, again, it seems to me.
I suppose that's fair. Sorry, I don't want to get too far off track. We can return to this in discussion, but sure there are certain varieties of cubists that would just deny, right, that
sure we will.
The ontology exists until yeah.
Okay, yeah. I'm sure we will, but I just want to say that. I mean, the reasoning, at least naively, seems to be very simple. You're just saying that you can make a measurement on one side that will guarantee that the value on the other side is determined. And if the locality holds, then the result on the other side must pre-exist to the measurement on the far away. In fact, it must pre-exist to the, whether we measure something or not. That's the point. We don't even have to measure something. So Schrödinger's theorem, again, it says that with the assumption, Hilbert space, self-adjoint matrices, then when you have this maximal integral state, there exists a non-contextual value map. Okay, that's what Schrödinger proved. Now, a few remarks. When Schrödinger derived this theorem, he was deeply puzzled by it. And that's why we call it Schrödinger paradox, even though he did not use that expression. Like EPR, Schrödinger took locality for granted. So they never thought of dilemma the way I speak of dilemma, because they just thought, it's obvious that locality is true, so that they thought that he had established an incompleteness of quantum mechanics even more radical than what EPR had claimed to have found. In the literature on quantum mechanics, the values taken by the map V are often called hidden variables because they complement the description of a physical state given by its quantum state. So a physical system, hidden variable is anything that would describe a particular quantum system beyond its quantum state. Any variable that you add to the quantum state for a given electron, let's say. But we prefer the term value map because the expression hidden variable, at least in our case, is a misnomer. The existence of this map leads what one might call the naive statistical interpretation of quantum mechanics. And in fact, it is sometimes sold as a statistical interpretation, which means that the state psi would be simply that for an ensemble of systems, each of which has psi as its quantum state, the statistical distribution of V of O would be given by 1/n for each possible value lambda k. So you prepare an ensemble of systems with the same quantum state, and then for this operator O, you have a value V of O, which is different from one particle to another, from one quantum system for another, but they have a statistical distribution, which is 1/n. Now, I think that if you really squeeze physicists on this question, what they have in the back, those who don't worry about quantum mechanics think it's all right, have in the back of their mind what I call the statistical interpretation, the naive statistical interpretation. So in fact, they're more realist than they should be, as we will see. But I think that's a fair description of what physicists actually think. And of course, if that was true, there would be no problem. A frequent objection to our theorem, and that's where we come back again to this subtle thing that we don't even need to do an experiment, is that if you take two non-commuting observable O tilde and O tilde prime, you can measure only one of them at a time, and the measurement of O tilde will in general affect the result of the measurement of O tilde prime. Hence goes the objection, one cannot attribute a value V of O to all observable at once, and this is maybe what Bohr was saying, because you can only measure O tilde or O tilde prime, not both, so you can't assume that there's a value V of O and V of O prime. But that assumption ignores the locality, this objection ignores the locality assumption, which implies that the choice of the experimentalist acting on system 2 cannot possibly affect the system, the properties of system 1. So whether the guy on the other side chooses to measure O tilde or O tilde prime doesn't matter, because whatever it does cannot affect the results, cannot affect the value of the observable O on Bob's side, and so these values must pre-exist. Schrödinger illustrated this with the following analogy. Suppose you have a large set of school children to which one of two questions can be asked. The question being similar to the choice between the two operators O tilde and O tilde prime. The question being chosen at random, say by coin tossing, and suppose that the children always give the correct answer to the question being asked of them. The correct answer here being the value V of O or V of O prime, which is determined by the measurement of O tilde or of O tilde prime. Would anybody doubt that this means that the children know the answer to both questions that they could possibly be asked, namely that the value V of O and V of O prime are predetermined, even though you ask only one question at a time? Would anybody suggest that the question being selected at random is precisely the one that they know the answer to, and that if the other question had been selected, they would not have been able to answer? Of course, it could happen by accident. Student passing an exam, we all know that, can be lucky and be given just the question to which they know the answer and not any other one. Although I think many people here are teachers, and you probably know that the students usually say that they just got the question to which they did not know the answer. They knew the answer to everything else, but not the question they were asked. Anyway, But if that experiment is repeated a very large number of times, the possibility of an accident becomes less and less likely. And here quantum mechanics predict that the correct answer, which is the value of V of O prime determined by the measurement of O tilde prime, will be given no matter how many times the experiment is repeated. I must say that this possibility that they only know the answer to one question, the one they are being asked, is a version of what we discussed last week, namely superdeterminism. That's basically what superdeterminism means. I think it doesn't make sense. And finally, we need a purely mathematical consequence of non-contextuality. The value map has the fundamental property that V of O is an eigenvalue of O. And if you have two commuting observable, then V of the product is V of the product is product of the V's, and V of the sum is the sum of the V's. That's simply because if it's non-contextual, so whichever way you choose to measure O prime or O plus O prime, must yield all the same result, and a valid quantum mechanical way to measure O prime or O plus O prime is to measure O and O prime separately and to take the product or the sum of the result. So that statement is, that property is analytical if we accept the existence of a non-contextual value map. And now there is finally a second mathematical fact which I invoke, which I don't prove, but is well known. It's a theorem going back to Gleason, Cock-and-Specker, Bell, Mermin, Perez, etc. If you take a finite dimensional Hilbert space of dimension at least 4, it could be 3 for some property, never mind, and A is the self-adjoint operator, then there does not exist a value map such that the property 1 is an eigenvalue, or when they commute, either this hold or that. So we don't need both. We need simply one of the two. That, I mean, there are the two properties before, but we need only one of these properties to rule out the possibility of a non-contextual value map, of a value map. And that, of course, means that non-contextual value maps simply do not exist. In particular, it means that the statistical interpretation makes no sense, because you can't have a probability distribution on things that don't exist. Okay? The statistical interpretation, psi, as a probability distribution of value V of O, and that doesn't exist. Now, the conclusion of Schrödinger's theorem, I should explain why I put quotation mark there, is because it's not a strict theorem in a mathematical sense, because we use the notion of experiment or measure, or, and that's not formally mathematically formalized, but it's certainly a physics theorem, while this is a purely mathematical theorem about matrices, basically in finite dimensional vector spaces. And the theorem on the non-existence of non-contextual value map, they contradict each other, since one theorem says locality plus perfect correlation implies the existence of a non-contextual value map, and the theorem here says such maps don't exist. So the assumption of one of the theorem must be false, because the reasoning is correct, so the assumption must be false. The theorem on the non-existence, the theorem here is a purely mathematical fact. To derive Schrödinger's theorem, we assume only the perfect correlation and locality. The perfect correlation are a well-verified consequence of quantum experiments. The only remaining assumption is locality, hence we can deduce non-locality theorem, the locality assumption is false. Therefore, I finish part of my talk, which is to prove that locality, I'm just looking at the time, but okay, that's okay. So now let me say a few words about what does non-locality entail. Well, first of all, the action that we have, if there are actions at a distance, is apparently instantaneous. The action on system 2 affects instantaneously the physical situation in system 1 and vice versa. The action extends arbitrarily far. The effect does not decrease with the distance between the particles. The effect is individuated. If a 1,000 system made of maximally entangled particle pairs acting on system 2 of one pair will affect instantaneously the physical situation in system 1 of that pair, but not the physical situation of any particle in another pair. So these two properties, of course, is very different from Newtonian mechanics, because, of course, Newtonian mechanics is also in some sense instantaneous. Gravitation, at least in the equation, classical mechanics act arbitrarily far, but the action, the effect decreases with the distance, and it's not individuated because every body is affected in the same way depending on its distance, while here it's only between pair of particles that are in entangled state. And finally, the action cannot be used to transmit messages since the results are random and uncontrollable. you have no way to use this perfect correlation to send a message because one side of the experiment cannot control what the result will be. The impossibility of sending messages is sometimes taken to mean that there is nothing non-local going on, but non-locality refers to the causal connection as described by physical theories, namely, there must be a causal connection between the two wings of the experiment, which I just proved, because if there isn't, then we get this non-contextual value map. Sending a message is something more anthropocentric than that, and requires that humans be able to control this interaction in order to communicate. The Big Bang and earthquake cannot be used to send messages, but their causal effects nevertheless, a remark I think made by Tim Maudlin, if I'm not mistaken. Now, what happens in Bohmian mechanics or in the Broglie-Bohm theory? I use often the word the Broglie-Bohm theory because it was not due entirely to the Broglie, but at least he introduced the idea, and is, in my view, especially in France, the more important French physicist of the 20th century and the most misrepresented, misunderstood, despised, etc. physicist of the 20th century also. So the complete state of a closed physical system with n particles is a pair where the quantum state, the usual quantum state, there is nothing else, and there is a vector of n component or 3n component, if you wish, which represent the position of the particles, and they exist independent of whether you look at them or you measure them, and each xi is a point in R3. These positions are called the hidden variable of the theory because, by definition, anything that describes a concrete system beyond the quantum state is called a hidden variable, but they are not at all hidden. It's only the particle position that you detect in any experiment. For example, take up the impact of the screen in the two-slit experiment. So the expression hidden variable is really a misnomer, at least in the context of the Broglie-Bohm theory. Both objects, the quantum state and the particle's position, evolve according to deterministic laws. The quantum states evolve according to Schrödinger's equation or a variant of that and guides the motion of the particle in the sense that the velocities of the particles are functions of the wave function. And the simplest case, the function is like this. You write the wave function as a radial part and an angle, and then the derivative of the position, which is the velocity of the kth particle, is simply the gradient with respect to xk of the phase that you have here. That's the simplest case, but that's enough for us. An illustration of the dynamic is given by this well-known figure, at least a figure which I hope now is rather well known in the two-slit experiment. Each particle goes through one slit because they have a position at all time, and each of these wiggly lines represent a trajectory of a particle with an initial point here, which is not easy to distinguish, but you can see that there are all these different lines. Now, these lines are, these are numerical solution of the Broglie-Bohm equation together with Schrödinger's equation. So the particle goes always through one of the slits. The wave function is a wave and it propagates in a sense to both slits. And then because there are two sources here of the wave, they interfere and then they produce these wiggly lines. And then you notice that on the second wall, there are places where there are almost no particles and places where lots of particles, okay? And so you get the interference pattern that you usually see when people describe the double slit experiment. Notice also there is a line in the middle here that the particles cannot cross. That's a property of the dynamics. And notice also that the lines are wiggly here when there is no force acting on the particle, just the wave function. And so the dynamics, if you wish, does not respect first law. Okay, it doesn't have to, but that's a fact. I think that's all I have to say about that. But then now comes the following thought. The Broglie-Bohm theory is deterministic, so the result of any quantum measurement will be determined beforehand by the quantum state and the configuration of the relevant system. Thus, for the Broglie-Bohm theory, there seems to be a value map, because everything is determined. So you say, how do you, the experimental predictions are the same as those of orthodox quantum mechanics. We saw it in this example, and it's true in every possible experiment. But then, of course, the value map that we have is actually contextual, and I want to explain that. Saying that it's contextual means it's not a real value map because it doesn't give a value of the value possessed by the particle, but it's something that depends on the context, namely on the measuring device. So we'll explain that with the example of spin. So to prove that it's contextual, it's enough to show two experiments measuring the same spin operator, getting different results for the same initial conditions of the particle. So, let's see, how am I doing? Okay. So consider a Stern-Gerlach apparatus measuring the spin, and H is the magnetic field. So the initial state is a certain function of Z. I don't write as a function, there's also an x-axis here, but I don't write it as a function of x, times a superposition of an up spin and a down spin, and the up and down is in the direction where the field is measuring, the spin. And I describe the wave function, the support of the wave function as a little disk, it's very artificial, and the position of the particle somewhere here, okay? So now the up part of the spin will always go in the direction of the field, and the down part will go in the opposite direction. That's as far as the wave functions are concerned. But if the particle here will actually go in the upper part, it will always go upwards because it's initially in the upper half of the support of the wave function. It's above this line. And why will it go? But for the same reason as I explained before, there are certain lines that particles cannot cross, and in this example, they cannot cross this middle line. Just the same way I explained a few slides before. Let me see if I can go back there. Here there was a line in the middle that particles could not cross, and the same phenomenon occurs. So that's just a property of the Broglie-Bohm dynamics, okay? Now repeat the same experiment, but with the direction of the field reverse, and let us assume that the particles start with exactly the same wave function and same position as before. So we have the same wave function here, and the particle starts here. And the field now is in the opposite direction. But the particle will still, it will still go upwards. But you see now it goes in the direction opposite to the field, so it will be labeled having its spin down, while before it had its spin up. So the particle whose spin was up a few slides before, here, it was up because it went in the direction of the field, now has its spin will have its spin down. Although you measure exactly the same quantity, the spin the vertical direction, with exactly the same initial condition for both the wave function and position of the particle, but with a different arrangement of the measuring device.
So I have a small comment.
Yeah.
Yeah.
You have to be careful here. Gerardi pointed a mistake in Dave Albert's description in this form. You have to, the Stern-Gerlach have a gradient.
Yes, yes, yes.
So you have to change one of them.
Yes.
You change both the gradient and the field, nothing will happen.
No,
usually if you,
I know. We discussed that already. I know. Okay, I want to keep it simple. Let's say it's the gradient of the field that is changed. Okay, that's in our paper. It's mentioned like that. Okay.
Okay.
But the point is that with two different arrangements of the apparatus measuring the same spin operator, you get different results. So the value map is contextual, or rather does not exist as a true value map. And the same thing can also explain or show the non-local character of the Broglie-Bohm theory, which of course it must be non-local, since we just showed that if there was it was local, it would have a non-contextual value map, and therefore it would lead to a contradiction. So now you do it with we start with a state, which is this entangled state, which I had before, a maximally entangled state, and you have particle A and B, Alice and Bob, if you wish, and they are sent to now, these planes which are perpendicular to that line. There's a magnetic field or gradient of magnetic field, and then the particle will either go in that direction or in that direction, etc. Okay. So in the boxes, the wave function split into two parts, one going in the direction of the field and the other the opposite direction. Now we have the dark dots for the position of the particles. And suppose we measure the spin of the A particle first, because I put this box closer to that one, if you wish. Then if the particle starts initially above the horizontal line in the middle of the figure, it will always go up, just as in the previous figure. And then it will go in the direction of the field. But since the wave function of two particles are such that they are anti-correlated, the B particle will have to go in the direction opposite to the one of the field, namely downwards. Now you could say, well, but the particle here starts above the middle line, so how comes it can go downwards? Well, the point is, after the A particle has been measured, it turns out that there is no symmetry anymore, and the particle, there is no line of symmetry anymore, and the B particle can go wherever it wants, up or down. It's not constrained to do that. Anyway, so that's what the particles do. Now change the orientation of the field on the side where you measure the A particle, or the gradient of the field, okay? But again, the A particle starts above, so it will have to go above, so it will have its spin down. But then what does the B particle do? The B particle, well, it's in the next slide, okay? It will go in the direction opposite to the field. But since the wave functions are anti-correlated, the B particle will have to go in the direction of the field. This goes the opposite direction. This has to go in the direction of the field, namely now upwards. And I have not changed anything to the direction of the field here. So if you remember the previous figure, this was going up, this was going down. You compare the two figures, here it goes down, and here the B particle goes up, and nothing has been changed to the experimental arrangement on this side, but things have been changed on this side. So by changing the orientation or the gradient of the field here, you change instantaneously the path followed by particle B over there. So if you do nothing on one side, but you change on the left, then it will affect the trajectory of the particle B. In one situation goes up, the other goes down, and that may be arbitrarily far away from the A particle. That's the way the action at a distance manifests itself in the Broglie-Bohm theory. So there is a genuine action at a distance here, since acting on the A particle by choosing how to measure its spin instantly affects the behavior of the B particle. The fact that the Broglie-Bohm theory is non-local is a quality rather than a defect, since we just show that any theory accounting for the quantum phenomena must be non-local. Now let me make some final remark. I think we're ahead in time. So in the literature on Bell's theorem, one often finds the assertion that this theorem forces us to give up either realism or locality. I say often to be polite, but I should have said almost always. And this is something which you find in many, many places. Now we have to discuss what that means. Realism viewed as a philosophical attitude can have different meanings. The weakest one being the rejection of solipsism. Solipsism says there is nothing outside my consciousness. Or radical skepticism, there is a reality out there, but it's unknowable. Realists contend that there is a world out there having objective properties, and that the goal of science is to discover those properties, and that sometimes they succeed. If that is what realism means, most physicists are realists. They believe in atoms, stars, galaxies, etc. They also believe that measuring devices indicate definite results at the end of an experiment. Otherwise, why would you believe quantum mechanics in the first place, since all the evidence for quantum mechanics comes from those results of experiments? So the meaning of realism in discussion of Bell's theorem must be different from those trivialities or generalities, and it often refers to what one might call microscopic realism, the idea that quantum objects have properties other than their quantum states. These properties, what are also called hidden variable, would provide what we call here a non-contextual value map. The main point of our paper, and of course many other people have made the same point, but it's not widely accepted, is to show that there is no choice to be made between the rejection of realism in this latter sense or locality, or rejection of locality, since the existence of these maps is a consequence of locality and of the perfect correlation. It's true that such non-contextual value map cannot exist, but in the perfect correlation are immediate consequences of quantum mechanics. The only logical conclusion is that locality is false. So realism in the sense of existence of a non-contextual value map is not an assumption of our reasoning, but a consequence of the assumption of locality and of the perfect correlation. Let me belabor the point by summarizing again the logic once more, and then you can keep that and show to your friends. If you have perfect correlation locality, there exists non-contextual value maps. There's a mathematical fact that those maps do not exist. Thus, either perfect correlation or locality is false. Perfect correlation are empirical facts, therefore locality is false. That's the whole logic of the paper. Now, as a point of history, it's very interesting to say that Bell exactly viewed his discovery in this way. And it's amazing the number of people in my university, for example, when I was a student, everybody was attributing to Bell results, which is the opposite of what he actually discusses. People quote Bell all the time without ever reading him. No, nobody has read him. When I got this book, I was fascinated. I read it practically without lifting my eyes from the book, because I was fascinated to see that at every page he says the opposite, more or less the opposite of what everybody says he says. You could of course say, you could say Bell says proposition P, I believe proposition non-P, and here he's writing Bell is wrong. But it's absurd to say that Bell has shown non-P when he says P, right? That's really irritating anyway. So because what they attribute Bell is has shown that local realism is false. Local realism, which means you have to choose between locality and realism. I never explain what that means, but anyway. Anyway, so here what he means by determinism in this quote is the idea that there exist pre-existing values, or what we call non-contextual value map. He says the limited degree to which determinism plays a role in the EPR argument is not assumed but inferred. What is held sacred is the principle of no action at a distance. It is remarkably difficult to get this point across, that what he calls determinism here, it's not the same thing as Laplace determinism, but anyway, it's not a presupposition of the analysis. And he was aware of the misunderstanding since he had it, but only in a footnote. He said, in my first paper on this subject, starts from a summary of the EPR argument from locality to deterministic hidden variable. But the commentators have almost universally reported that it begins with deterministic hidden variable. Almost everybody says, Bell assumes that they're hidden variable. No, he assumed that locality is true. Of course, this footnote did not stop the misunderstandings, to put it mildly. To come back to the EPR dilemma, do measurements reveal or create reality indicated by their results? The answer is that in general, they do create that reality. They don't create that reality if you measure the position, but for every other observable, the measurement will always be contextual, and I explain in the example of spin. But they do it in a non-local way. The important lesson coming from our discussion here is, that's a final remark, is the concept of measurements, that it appears in the traditional formulation of quantum theory, can have often a deleterious effect upon one's thinking and tend to cloud the issues. Here is John Bell on the topic. I suspect physicists were misled by the use of the word measurement in contemporary theory. This word very strongly suggests the ascertaining of some pre-existing property of something. I mean, if I measure the length of my table here, I presume that my table has a length before I measure it. And that's true for everything they use the word measurement. But quantum experiments are just not like that, as we learned from Bohr. The results have to be regarded as the joint product of system and apparatus, the complete experimental setup. The use of the word measurement, or the misuse, makes it easy to forget this, and then expect that the result of measurement should obey some simple logic in which the apparatus is not mentioned. And that's the source of all what we call quantum logic or quantum probability. And the sort of simple logic is like the V of O plus O prime is V of O plus V of O prime, etc., etc. You know, all these rules seem pretty natural if you forget the role of the measuring device. And it would be better to, says Bell, to ban it in favor of the word experiment. In the Broglie-Bohm theory, you see exactly what's going on. It is a realistic theory in the sense that particles have objective properties at all times, not just when observed. The particle's description includes more than just their quantum states, namely also their position. Yet at the same time, in accord with Bell's suggestion, analysis of the experiments that are usually called measurements, but would better be called measurements quotation mark, of a particle or system shows that the latter are contextual. They do not reveal a pre-existing property of the particle, but are genuine interaction between system and measuring apparatus that yield result reflecting the state of the apparatus as well as that of the system. The state of the apparatus being that the orientation of the gradient of the field could be either in one direction or the opposite one, giving different results. Now, for those, now I'm finished, and to do some advertisement for those who read French, this book is about, I mean, it has come out already, but the bookstore being closed, you don't have it in the bookstores. And if you want a more complete book where I discuss, for my viewpoint, at least on these things, that's the book which was written a few years ago and which gives more details. And then here, I have some remark on the construction of the operator or tilde, etc. But I think I will skip that. I mean, I will leave you the slides. If you want, we can discuss it. And then I have references. I have a long list of references and reference to our papers, but I think it's maybe better to stop here and start the discussion. I can go to the proof if you're interested, but I was thinking of stopping now. Okay.
Thank you. So as anticipated, I'm going to let Kim and Sheldon Goldstein intervene if they want to, if they have comments or questions. And then in the meantime, if you have questions or follow-up, please write on the chat group so that I can have the list of your names in the right order.
Should I start?
Yeah, whenever you like, thank you.
Yeah, so, well, if anybody expected me to like object to Jean, that was a miscalculation. Of course, I agree with everything he said. I do have some comments for what they're worth. There are two comments about history, one about long history and one about more recent history. The one about long history is something that Jean said, which is that the Schrödinger paper, which was his reaction to the EPR paper, and it's a wonderful paper, right? It seems not to have been much read. Everybody's heard about Schrödinger's cat, but as far as I can tell, vanishingly small numbers of physicists have ever opened that paper and looked at it.
Exactly.
And it does contain within it lots more. I mean, first of all, it contains the cat experiment and the point of which people have completely misunderstood. But it also contains these technical results about maximally entangled states. And it's all just sitting there in 1935. And what Jean's showing is that just thinking that through in the right way, which Schrödinger really didn't get that far, you get to non-locality. So one thing is just to really recommend to anybody who hasn't studied that paper that you sit down and really read it carefully, beautifully written, nice, punchy, intuitive examples, and so on. The second is about more recent history, a history that I lived through, although some people on this call weren't around for it. And that was the psychological effect of the realization that you could get a non-locality proof that did not involve non-trivial probabilities, where all the probabilities were ones and zeros. And for most of us, maybe all of us, I'm not sure, the first such example was the Greenberger-Horn-Zeilinger example. And it's a bit different than this. It's not what Schrödinger did. It's very clean. It's very nice. I remember David Mermin, when he wrote about it, just said that until that time, and Mermin had thought as much about Bell's paper as anybody, and he always said he had a suspicion that somehow Bell's result relied essentially on probabilism and statistics. Because Bell's original result really is about long-term statistics of experiments. And then when he saw the GHZ result, he just said, no, I was wrong, right? I mean, this is all ones and zeros, perfect correlations. And it did have the useful result of just closing down a certain, not set of arguments, because nobody ever gave any arguments, but a set of suspicions that somehow fundamental indeterminism was playing a central role here, and it isn't, right? And I guess the third remark I want to make, which I think is borne out by doing all this through the GHZ argument, which is what I tend to do these days. And this is now a question of taste, but I think it's worth mentioning, is that if you do it through the GHZ argument, you don't go into any formalism of quantum mechanics at all, right? You don't talk about Hermitian operators. You don't talk about contextualism or non-contextualism. None of it even comes up, right? It's just, here's some experiments. You know, here are 3 people. Each person has 2 choices of how they orient some device. Call that an experiment that has an outcome. Whether it's a measurement, who cares, right? Whether it's contextual or non-contextual, who cares? Doesn't matter, right? Those terms don't even arise. You don't have to worry about talking about measuring Hermitian operators, and that's where all this contextual, non-contextual terminology comes in, and talk about measurement comes in. But you can do the whole thing from beginning to end without mentioning any of that stuff. And it's important that you do it that way, because Bell's theorem is not about quantum mechanics, right? It is just not about quantum mechanics. It's about locality. And so you need different tools. I mean, it's a weird thing that it's been so hard to get Bell's result across to people. And it has been, and it continues to be. And it's as much a puzzle to me as how 69 million Americans can vote for Trump, right? I can't explain it, but there you are. And so you need different tools to try and get the point across to different people. And maybe some people feel more comfortable with the quantum mechanical formalism, and it somehow will convince them if you lay it all out in terms of Hermitian operators and blah, blah, blah. To me, it's just the opposite. I'm more convinced when you don't touch the formalism and you just talk about, here are some experiments you can do, and here's the results that are predicted, and my God, there ain't no local theory that can make these predictions. And so I guess, the other just piece of advice is if there's some small technical piece of this that you're worried about, is just look at the other, because there are a bunch of different ways to get to this result, and they go through different routes. And you ought to find one that'll convince you. And if you're just nitpicking at this stuff, at this point, you've missed the point. So that's, none of this is any objection at all to what Jean did. It's just putting it maybe in a slightly larger context. And I think that's all I have to comment about it.
Yeah, can I answer?
Sure.
So, well, yeah, I mean, I'm not so familiar with the GAZ, but in my book, I give the argument by Goldstein and Zangi, which is very simple, with 3 different orientations of the spin in different directions. And of course, there you use statistics, that's true.
Yeah.
It's very simple. You just show that you have a correlation which are 25%, and then, it's a very simple argument.
Yeah.
I think it's simpler. I think this one is nice. I mean, of course, if I write for physicists, I don't find it's too much to ask that they be able to know something about finite dimensional matrices. I mean, this is not high level mathematics. And then we have another paper where we use the argument, the original EPR variable, and use another no hidden variable theorem to prove in the EPR, in the usual EPR variable, namely position and velocity, that you could also prove without using Bohm variable. So if you wish, it's a little bit of mathematics, but it's a little bit of, but I mean, it wouldn't be the simple, I wouldn't probably use this argument if I taught it to students, and in my book, I don't mention that, I use the simpler argument. Whether GAZ is simpler, I don't know. The problem I have with GAZ, I guess, is that I don't like the way Z interprets quantum mechanics. So
yeah, okay, but that's not fair, right? I mean, the argument's the argument.
But you see,
give it in 5 minutes and it's perfectly correct. So
yeah, it's perfectly correct, I'm sure. But then, of course, Mermin also had discussion with Mermin and Bielefeld, and he's not clear. He's not clear about what the consequences are. He says that people.
I'm not here to psychoanalyze David Mermin beyond noticing that the GHZ argument did make a deep impression on him. right?
Yeah, that's so.
Because it was all ones and zeros.
Yes, but do either of them, okay, but let me ask you, since I'm not so familiar, do either of them think that they have proven non-locality, or they have proven no realism, or what do they think?
Look, Merman is too complicated a figure for me to comment on. Greenberger, I've talked to a couple times. I didn't ask him directly. I guess maybe somebody has. I assume he understands what he proved. I think he knows he proved non-locality.
And Zeidinger?
Zeilinger, I haven't talked to, but you know, I don't want to get into, again, I'm talking about proofs. I'm not talking about.
No. I'm asking another question. I understand.
Yeah, I don't know. I haven't talked to Zeilinger.
Curiosity, let's say. It's a curiosity. It's not an.
Yeah. I don't know.
You.
The answer is I don't know. Maybe somebody else here knows.
Yeah. Anyway, the way you got dragged into this discussion, because last time we had one more paper discussed, which was discussing, you know, value. What was that? Outcome independence.
Yeah.
Parameter independence and so on. And at least in this version and in this other version, all this I remember seeing either in your book or your paper a discussion of these, you know, distinctions that were not real distinction, I think. And that's how I mentioned your name last week in this seminar. I mean, I think this paper shows that there is no such discussion to be had. I mean, and the other papers also. I mean, I'm sure, but this is completely passé. This parameter independence and outcome independence, I think.
Okay, so thank you both. Thank you, Tim. There's a list of people, but at any point the co-author wants to jump in, please do. So the first question I have is from Aurélien.
Can I jump in for a second?
Sure.
And by the way, when you see me, I'm going to have to leave very soon because I have a class in a few minutes that I have to give. I want to make a little comment on just a short statement that Tim made. Not that I disagree with it at all. I agree with everything these two guys said. Of course, I agree with Jonathan, the co-author of the paper.
Well, it's
I, of course, agree with what Tim said, since Tim agreed with John anyway. But you said, I don't remember. I didn't get much sleep the last 2 nights. Most of you know why. So I may be totally incoherent. But Tim said something like, you know, Schrödinger didn't get that far, something like that. What did you remember the exact words you used, Tim?
I think I said he didn't get as far as to get non-locality.
Yeah, I would have, that's correct, of course, but I would have said it, he didn't get quite that far, because if you look at how far he did get, he was almost there. He was epsilon. So I just want to make that little comment. And then one other comment, and this is what, yeah. That's what, so that, let me underline again something John stressed and something Tim stressed. That is a wonderful paper. People should all read it and understand it, the Schrödinger paper. Called the cat paper, although the cat is just one paragraph. And it's, in some sense, not at all the most impressive part of the paper. One other small comment. Historical, something that needs looking into. Probably a lot of people have looked into it. What I find so difficult to understand, just as I have trouble understanding Trump voters, and I think there might be a common phenomenon here. Why, I can't understand, why is it that people are willing to accept such utterly weird stuff in connection with quantum mechanics, things that they hardly understand what it means, but they say, well, how can we know how the world is anyway? So maybe it's like that, even though I can't even quite understand what that means. Like reality is non-commutative. We know what it means to be non-commutative in mathematics, but nobody knows what it means for reality to be non-commutative in a coherent way. But physicists were willing to accept all that stuff, but there was such profound resistance to non-locality, even though that's one of the clearest conclusions of quantum mechanics. I find that striking and something that ought to be subject to historical analysis. And that's all I have to say.
Well, but non-locality is a difficult pill to swallow, I think.
Non-reality should be a difficult thing to swallow as well.
Yeah. You know very well that we both agree on that. That's not That's not the issue, but you know, given that you're a realist and blah, 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 I mean, still, non-locality is very difficult to swallow. I found it very difficult.
It is, but it's a contrast between that difficult thing to swallow and the far more difficult things that you would think to swallow, that physicists were very happy to swallow.
Yeah, but the problem is that you never know what they really mean by that, you're saying.
Yeah, so if it's vague enough and mystical enough, maybe they're happy to swallow it.
I think so, yeah. The non-locality is something pretty clear. And what I like in the Broglie-Bohm theory is that you see exactly how it works out.
So the lesson could be, the recommendation could be, if you want to succeed in foundations of physics, try not to be too clear.
Okay, I hope I did not succeed in that.
Thank you, Sheldon. There's a thing from Jeremy about this exchange. I'm going to ask you to keep it as short as possible because I have a long list of questions. Thank you.
Okay, well, we have next week still, huh?
Yes, and I forgot to mention, there is next week, which is going to be dedicated just to free discussion, so there's no talk or anything, and it's just 2 hours of anarchic discussion. So, but I guess not everyone can join next week, so let's try to. Anyway, Jeremy, if you want to ask your follow-up.
Yeah, thanks for this exchange. And look, maybe this is just like a quick rhetorical point, right? Like, you know, in the wake of the election, right? Like for me, when I'm taking out this is like, it's startling that half of Americans lack so much epistemic humility, you know? They have to have their ideology enforced to the level of the federal government, like, and this sort of epistemic humility, this lack of epistemic humility is the same sort of thing that I'm feeling in this discussion right now in terms of not considering realist local proposals, right? Like these arguments are also very simple on the realist local side, right? Like you pick up David Wallace's book and there's one page and one space-time diagram. And that's the argument for this local realist approach. Look, far be it to say that we have to accept this theory, but why not consider it, right? Why not at least put it in the discussion here?
Can I say something to that? If I understand what you're saying, you're suggesting that Everett is local. It isn't.
That's the point, yeah. I was going to say that.
It is not local. Nobody ever has written down a theory of branching that is local. Branching is in the wave function. The wave function is not a local object. The wave function does not take the speed of light to branch. You
well, why not impose that?
You can't put the wave function on a space-time diagram. It's not a local thing.
Well, yeah, but nobody's proposing to put the wave function on a space-time diagram, right? We're saying that
let me say one thing. The point in when you have the wave function ontology, there is no space-time. There's no space-time. There is an abstract mathematical object in a Hilbert space. That's all.
Okay. Right. So now there might be interesting points of contrast, right? Maybe there's an interesting point of contrast if we're taking ourselves to be wave function realists, right? Or if we're taking ourselves to, demand that locality be understood in a certain way, right? Like local influence has to be measured in terms of statistical consequences. Fine, right? I'm just saying these things clearly ought to be explicit and on the table if we're going to try to be arguing that we're forced to accept locality or we're not.
Let me make one more comment. Sean Carroll is as much an Everettian as anybody. Ask him, he'll say, yeah, it's completely non-local theory.
I totally agree. And Sean Carroll has a strange many worlds view, right? But there are plenty of many worlds theory that are perfectly local.
Worlds view that's ever been articulated.
Of course there is.
No, there isn't.
It's in one page in Wallace.
No, there's not there's not a coherent view articulated anywhere in Wallace.
All right. Well,
Actually,
this is
not one that will connect up to actual experience. There certainly is not, because he doesn't have any theory of what we would call local beables. He has no account at all of how anything that we would call a laboratory with a box in it and a flash on a screen that happens above or below a line happens. Nowhere. Nowhere. From one end of that book to the other.
So this is something that strikes me as strange because I think it's very clear to me what the local beables are, right?
What is it? You tell me.
They're just the emergent branch entities, right? Like
what does that mean? Emergent from what? Local in what?
Emergent from the quantum dynamics, right? And like the story is
what
not
does
even
that mean?
controversial. It's not even that controversial because everybody accepts decoherence anyway as playing some role.
Do me a favor and try and define a single term you just used. What does emergent mean?
What does emergent? Okay.
Oh, sorry.
Yeah. This is maybe going too far.
As much as I'm enjoying this, and trust me, I am. I have to. We have 45 minutes and a lot of questions. But next week, please come and we can discuss about this, among other things. So I go back to Aurélien. Unless, sorry, there is one thing I have to do. I want to give the opportunity to the authors to intervene on this if they want to. So Jan and Sheldon. Otherwise, I'm just go for the question as you prefer.
No, I won't say anything more than what, but maybe Shelley has something to say about many worlds and locality. But I mean, because Shelley and others, I mean, Allori and I forget what the list exactly is, I've written a paper on Schrödinger first theory in the many worlds, where they actually put variables, an ontology on top of the wave function. It's not a pure wave function ontology, but there's an ontology localized in space-time. And in that theory, the question of locality can be asked, and the theory is, of course, non-local. It's also very strange, but that's a separate question.
It's non-local, but in a pretty subtle way.
Can you explain?
No, I can't explain. I can say, though, historically, that we first thought the theory was local. Then thinking about it more carefully, we decided we were wrong. It's non-local. I'm not sure we ever had a version of the paper where our conclusion was the theory was local, but that's even possible. Then we say, oh, we better change it to say it's non-local. So it's a little tricky, but I don't remember details now.
Okay, thank you. Aurélien, finally, sorry for waiting so much.
It's fine. Okay, well, I have not so many remarks, but I have a question about the relation between the work of Jean and also the work of David Mermin, because you mentioned
of who? The work of whom?
David Mermin, because you mentioned before Mermin works concerning GHZ, and also, but you also know that he was involved in the study of non-contextuality, and especially about the Cohen-Specker theorem. And there's one paper in the early 90s, the TRL paper, where he somehow, I think, discussed very similar things in the new paper. I'm not really sure the argument is exactly the same, but he's comparing Bell theorem, GHZ, and Cohen-Specker theorem, and the same kind of reasoning, deduction is appearing in some lines in the paper, telling that if you want to derive the, let's say, you use locality to construct what you call non-contextual value map, and then you use the Cohen-Specker theorem, you get a contradiction, you get a loop. And the way to say that is that, of course, it means that locality is wrong. So this is what you are somehow telling. But what he's claiming as well is that the way of proving the Cohen-Specker theorem is difficult because you use already non-local features in the paper. So you assume from the start the non-locality in the proof if you want to apply the Cohen-Specker to the structure that you are the Bell configuration with two observers. So which are disconnected outside of the light cone, let's say, as you mentioned. So I'm really believing that as Tim Maudlin was telling, it's important to consider the role of maybe of the work of Mermin, but also in the context of Cohen-Specker and so the GIZ and all these things. I think you also discussed, by the way, the problem theories of GIZ here in the same paper. Yeah. So maybe it's relevant for the discussion, and this is my most important remark. And my second remark is that you mentioned it in your talk, the local causality. You focus on causality, but there's also the role of you focus on locality, but there's in the Bell theorem it's impossible to separate this two arguments, locality and causality. So at the end, when you have Bell theorem, you don't know if the non-locality has to be true, like in Bohmian mechanics, which I advocate as well, but or it could be something else, like superdeterminism or retrocausality, or maybe something else. Of course, I don't speak about non-realism, because non-realism, I don't know what it is. Maybe it's like Trump telling them pandemic doesn't exist. I don't know. But the rest is, yeah, that's all.
Yeah, I don't know. I'm not sure what to reply, because I did not understand if your first comment was meant to be an objection to what I said.
It's not an objection. It's not an objection, but I think it's relevant to read the paper because of David Mermin. I have the reference here. I could even share the screen, but we have no time for that. It's a PRL paper, volume 65, number 27. The title is Simple Unified Form for the Major Non-Eigen Variable Theorem. This is one of his most famous papers, I guess, and he's really focusing on the non-contextual value map problem. And he's speaking about GIZ and Bell theorem, and he's making the connection between all these results. So
can you send it to me?
I have to be prudent because the paper is long, so this one is very short, so I have to.
Can you send it to me?
Yes, of course, I can send it to everyone. Maybe, okay, no, I don't know if I have.
Please send the link. Send the link.
I think I can do it in different. I think I can share a PDF now in that structure. I don't know. Partage, converser. Yes. Wait, converser. Yeah.
Can I just make a terminological comment here?
Sure.
The term non-contextual and non-contextual, the way it's normally used is again tied to the standard quantum mechanical formalism. So take the very example that Jean talked about, that David Albert talks about in his book. You have a Stern-Gerlach apparatus, and you can have it set up a certain way, and then you can have it set up the same way and change the polarity of the magnets, or have it set up the same way and change the geometry of the magnets, right? And Lev is right, you don't want to change both the geometry and the polarity, and all of those experiments are described as it were you use the same Hermitian operator to represent them. And then people say, oh, in a non-contextual theory, you should make the same predictions no matter how you do it. But that's kind of, you would say, why would you think that? Because they're obviously different experiments, right? I mean, there's no physical principle that tells you that if you change the polarity of your magnets, you ought to get the same result that you would have gotten if you hadn't changed the polarity. Or if you change the geometry, you ought to get the same result as if you hadn't changed the geometry. Okay? So for contextuality, if you just try and separate it from this pre-commitment to taking Hermitian operators as having some deep meaning, all it says is how experiments are done, how they come out depends on how they're done, which is kind of trivial. Where it becomes non-trivial is when the outcome in Bob's lab depends upon how the experiment is done in Alice's lab. And Alice is you know, megaparsecs away. That's non-locality. But the contextual, non-contextual distinction is not a fundamental physical distinction. It's a distinction that is tied to already accepting a bunch of quantum mechanical formalism and thinking about it a certain way. And you know, you get rid of that. Just think in terms of experiments, right? What does the theory tell me if this experiment is done, if this experiment is done, if this experiment is done? And the word contextual, non-contextual will never appear from beginning to end of the analysis. The question is just, according to the theory, would the experiment come out differently if Alice's experiment, far, far away, had been different, for example?
Unless there are follow-ups on this, I'm going to move to the next one. It was Ippo.
It's my turn. There is Alberto before, right?
Thank you. Yeah, you skipped me.
Oh, Alberto, sorry.
No problem.
And you were written on the list, so sorry about that.
Now, first of all, I wanted to thank Jean for the presentation, because I truly didn't know the rest of the content of the famous Schrödinger paper. It's true, we don't read it enough. So that's first of all, thank you very much. I had two detailed questions. The first one is on the formalism of the O and O prime or O tilde operators. I looked at the Schrödinger paper while you were speaking, and he uses a different formalism. He identifies the operators of Alice and Bob, but he doesn't show the algebraic formalism that you have used. So I'm curious to know where first it was introduced, as I would like to read that as well. It looks quite relevant. The second question is about the illustration you showed. You showed only the trajectories on the right side of the double slit.
Yes.
So my question is, in that simulation, what's on the left? Are all the particles centered on the separation line continuation to the left, as in a real experiment, or are they distributed along the vertical to the line? And if they are distributed, what kind of distribution they have? They have a Gaussian distribution, they have a equiprobability distribution. Do you know?
Well, there are different pictures. Depending on which distribution you assume behind the line, you can assume a Gaussian distribution or uniform distribution. I'm not sure what the assumption is in this picture, but of course you just start with these assumptions and then you draw the lines. The line will be different for different distributions, and then you always be qualitatively similar.
Yeah,
I have both distribution in my book, but I forget now which is which. I mean, which.
I never seen, the reason I'm asking is I never seen a simulation where on the left you have a real experiment distribution, which are all the particles in the center. And so if there is one, I would certainly be curious to look at it. If you find out, please let me know.
Well, I can send you, I think I have to find it, but there is a guy named Gondrin, a French.
Gondrin, yeah, I know the Gondrin simulation, yeah. He's not centered to the middle line.
But you can ask him to do it.
Yeah, I already did.
And he doesn't do, he cannot do it? Or?
I don't know if he's gonna do it. His son does the simulations.
Yeah,
yeah,
I'm talking about the son, yes, Alexander,
yeah. I will, if he does it, I will find out, yeah. I'm in touch with him.
Okay.
And about the O prime operators, do you know where first they were introduced in matrix form? And
maybe Shelley remembers, but I don't remember if he's still there, but I don't remember the Schrödinger paper offhand like this. I mean, I only remember the way we've rephrased it, but...
it's interesting. That's interesting, the way you have rephrased it.
I'm afraid Sheldon left.
Okay. We can send him an email. Thank you.
The next one is Ippo this time.
Yeah, thank you for the talk, Jean. So I have two remarks. One is more historical, philosophical, and the other is more technical on the proof. The first one is maybe not only for Jean, for any people who knows about the history of Bell theorem or Bohm. So a couple of years ago, I made some historical work on the Cohen-Specker theorem, quantum contextuality, and also the other Bell papers that is not well known on the problem of hidden variables of quantum mechanics. So I don't know if everybody knows about this paper. So there is a Bell paper on the EPR paradox, but it's not the first paper actually that Bell wrote on the hidden variables. He wrote a previous one on that was meant to prove that hidden variables were possible in the first place, because his motivation was to in a sense, there was this proof by Feynman that said that hidden variables are impossible, and the fact that Bohmian mechanics were there was quite astonishing for Bell, and he decided to look into that, and he wanted to show that no, it's possible to have hidden variables in quantum theory. And so one of the motivation of Bell was that he was kind of against what the Copenhagen interpretation, if I don't really like this, because I don't know what Copenhagen interpretation is, but he was against, let's say, Bohr and stuff like guys like this. And in what you show, Jean, Bell is like, I mean, to justify his theorem, to justify the contextuality in some kind of in hidden variables, he's referencing to Bohr. He says, as we learn from Bohr. And I think it's quite weird, right? And I don't understand why he does that. It's quite paradoxical or ironic to me that he started this work to go against Copenhagen, Bohr, and these guys. And here he makes some kind of step back, saying that as we learn from them, hidden variables should be contextual in a sense. So I don't know what people think about that. It's quite astonishing from me. I don't know what you think, Jean, about this fact. That first, it seems that Bell was against Copenhagen, and here he said that we learn from Bohr. And I don't
wait. Okay. He certainly has been always against Copenhagen. If by Copenhagen you mean that quantum mechanics is only about laboratory measurements and something like that. And he always criticized Bohr, but what he did say, which Bohr said, is that the measuring device and the system are inseparable wholes. So you can't separate both. And in the Broglie-Bohm theory, it's in the equation. You see why you cannot separate, why one measuring device interacts non-trivially with the system which is supposed to be measured. It's only in the context of misuse of the word measurement and in the fact that you have this, action of the measuring device on the system. I mean, the orientation of the field in my experiment determines the result changes the result of the measurement, and so the measurement's not a real measurement. But I don't think Bohr had any, how can I say, he had no argument, was sort of a priori that he said that. And it's only that particular aspect of what Bohr said that Bell agrees with. Now, if you take his book here, I don't know if you see it here.
Yeah, the Bell book, yeah.
Yeah, Bell's book. There are two papers, okay, in the beginning. The problem of hidden variables, and the other is on the EPR paradox.
Yeah.
EPR paradox, the famous one where he proves non-locality, if you wish, and the other one is on the problem of hidden variables, where he does actually refute
Neumann proofs, yeah.
Von Neumann and Jauch and Piron and so on.
Yeah.
But then he goes to show that there is something correct based on Gleason's theorem. So yes, his own, when I speak of the no hidden variable theorem of Bell, I refer to this paper. But then he also explained that if the theory is non-local, as the Broglie-Bohm theory is, then you can have a hidden variable theory. So he understands everything from the beginning, except that he did not have a proof of non-locality. The proof of non-locality comes in the second paper.
Yeah, okay.
But the first paper is showing that you can have hidden variables, in fact, and that the arguments against hidden variable contain unjustifiable assumption unless you do it in the way that Gleason did it, which is pretty abstract, but it amounts to no hidden variable theorem, which is legitimate, you see.
Okay.
Yeah. Can I just make a comment since Jean has the book? If you want to understand, Bell actually had a lot of more sympathy for some of the stuff Bohr said than even Jean said. And if you want to understand that, there are two things you should read. You should read The Theory of Local Beables, and you should read Against Measurement. And at the end of Against Measurement, Bell makes this very clear. In his understanding, when Bohr said you must describe the laboratory situation in classical terms, you must. Bell says that's where Bohr introduces local beables, in addition to the wave function. His complaint against Bohr is that they're only defined at macroscopic scale.
Yeah.
And what Bell then does is he says, if you just take away that restraint and you say you ought to have your macroscopic local beables be nothing but collections of microscopic local beables, have them defined at all scales, then you see that in that way of doing it, Copenhagen becomes Bohm.
Mm.
Okay.
So if you have to put those two papers together, right? Put together the theory of local beables and the programmatic importance of local beables for Bell, together with what he says about Bohr's insistence on there being a classical language, and it's in those two papers.
Okay, thank you. And so more technical. I don't know if it's a remark or a question. I don't know how I'm going to formulate that, but so it's kind of about contextuality, how you use contextuality. So what your proof is that quantum theory, you have a new proof, correct me if I'm wrong, but what you want with this paper is to show that you have some kind of proof that quantum theory is non-local, right?
That reality is non-local.
Okay, so here's my point. I have not an objection on the proof, but an objection on this claim. Because as maybe Tim and Aurélien already said, the fact that you're using the kind of the contextual hidden variable stuff on you're using the Cohen-Specker theorem in a sense, and the Cohen-Specker theorem is about Hilbert spaces. It's about projective measurement. It's about quantum mechanics. While the Bell theorem is theory independent. Bell theorem is stronger than Cohen-Specker theorem in this sense because you have Bell theorem, you have Bell inequality, and it's model independent, theory dependent. You can violate an inequality with projective measurement, but you can also violate a Bell inequality with noisy measurement, non-quantum measurement if you want. It's completely model independent, and so you can do it in the lab, check in the lab that you violate the Bell inequality and say, okay, nature is non-local. The Cohen-Specker theorem is about projective measurement in a Hilbert space. It's not working with noisy measurements. So you cannot, in a way, you cannot really prove experimentally Cohen-Specker theorem because it's about the mathematical structure of quantum mechanics. And so the fact that you're using it in your proof doesn't mean that your proof is wrong, not at all. It just means that you're showing that quantum mechanics is non-local, but you're not showing that nature is non-local, in my view. So I don't know, maybe you disagree with that, but and another point is that sorry, I just finished. In the quantum foundation field, what we call contextuality is really about Cohen-Specker theorem in a sense, and then there was some generalization that tried to generalize it to independent model and stuff like this by Speckens and guys like this. But when we talk about contextuality, what we define by the context is the a set of compatible observables that commute with each other. We have a mathematical definition of what a context is. In what you show here, your definition of context is more general, right? You include the fact that you can measure the same observable with different contexts. By different contexts, you mean different measurement apparatus, but this is not mathematically formalized. And this is also a point is that, so it works in Bohmian mechanics because in Bohmian mechanics, you have this kind of behavior, right? But in quantum theory, you don't need that. In quantum theory, you have quantum contextuality for dimension for at least 3. But if you do this, if you use this broader sense of contextuality, you can have contextuality like in Bohmian mechanics for dimension 2. And it's something that is not present in quantum mechanics at the beginning. So I know that it's present in Bohmian mechanics. But if you want a proof of quantum contextual of non-locality of quantum mechanics using quantum contextuality, then you have to define what the context is, and the context has a mathematical definition, at least in the quantum foundation field. So maybe you should. It's just a suggestion. Maybe you should add some details about what you mean by context and stuff like this.
Okay, I don't quite agree that we don't prove non-locality, because the only facts, if you wish, that we use are the perfect correlation. I mean, in a sense, it's like Bell's prediction or any or GHZ prediction. In the end, you have some experiments to check. You have to do something with zeros and one or some statistics or something. But nevertheless, the only thing which is important in our reasoning are certain facts about perfect correlation between different observables. All the formalism that I introduce is just part of a reasoning, but the input, the empirical input, are the perfect correlation in my argument. And
you start from I agree. You start from empirical inputs, but then you use a mathematical argument that is about quantum mechanics. So you make assumptions that quantum mechanics is correct.
No,
and when you do an experiment, you don't do that.
No. I'm only making the assumption that quantum mechanics is correct about the perfect correlation. Of course, Bell is also assuming that the quantum mechanics is correct about the correlation when you do measurements in different direction. And GSW is assuming that quantum mechanics, everybody is assuming that at some point quantum mechanics is correct, but not the whole structure. I'm using the structure of quantum mechanics in the reasoning, but the input in the argument, the empirical data that I use are only the perfect correlation. Now you could tell me maybe the perfect correlations are not true and then quantum mechanics is very badly wrong. That's possible. But you will have to say that in order to avoid the conclusion of non-locality for nature, not for a theory, nature. If nature satisfies this perfect correlation, then nature is non-local. And the whole thing is just an argument. I mean, the whole, my own rigmarole is just an argument to go from those facts to non-locality. I'm not assuming any prediction of quantum mechanics except that. But of course, you could deny the perfect correlation. I think there is no empirical evidence for that, but you could deny it.
I'm sorry, I'm not completely convinced, but I will try to think about this, and maybe next week where
Okay.
Thank
you. Okay.
Next one is Lev.
Okay. First, may I remark that Christian asked me if I would like to talk in this forum, and this brief discussion on many words make me wanted to present many words, because I think there is kind of a big misunderstanding, at least in some parts. Well, what does it mean? Now, another, I think, things which have to be clarified is the issue of non-locality. And for example, a many word is non-local, but many word does not have action at a distance. And I understand in the John talk, the non-locality is action at a distance. And so there is non-locality in a sense that local description, the sum of local description describe everything. This is local theory. And in fact, there is a claim that there is one like this, or maybe there is one like this, is Deutsch-Haydn. Maybe sometimes I will say, I will be ready to talk why I don't like it. Deutsch-Haydn theory is completely local. Many word is not local. The wave function is not local. It's everywhere. It has connection, but it has no action at a distance. And now maybe here a remark to Tim, who says, I understand that if Tim talks about not accepting non-locality, why so strange? I think there are very deep thinkers which were not ready to accept non-locality. Newton was extremely against non-locality. Even he had the non-local theory. He said it's unacceptable. Einstein said it's unacceptable. So this action at a distance is very, I think it's very natural that people are really against non-locality. So now about the talk. I haven't read the whole Schrödinger paper about cat. Of course, I look on this cat stuff, and all what I had from John, for me it was EPR. I didn't see anything new. Of course, maybe it's EPR toward Bohm. You had another example, not XP, but some other example. But the whole discussion of EPR, it's exactly this. Alice measures, and then she knows what's on both sides, and she can measure different things. So these things on both sides have local realities. They're real. So this part, I think it's EPR, and I don't think that Schrödinger had something new about this. What was missing to make it non-local, and I believe Bell was first to do this, is to find proof that you cannot find behind quantum theory something which will make local description. What you quote, all this mathematical statement, it's like Cauchy-Specker and other things, they can also very late, and they're necessary to add to this what EPR or Schrödinger saw to see that we have non-locality. Because in EPR, they say they didn't really know, but they hope that there is something behind which is local, and we needed the structure that it's really impossible. So I think that there is this connection to this later work which make non-locality. The paper by Schrödinger itself is not enough. And I think during your talk, John, you kind of make a remarks, and from your point of view, that many words doesn't solve, and it's kind of your claim is kind of universal. And I think the place where you can see the difference, you consider a dilemma. You said that Alice makes a measurement and she might reveal an outcome or she might create an outcome. According to many words, she creates two outcomes. And at the moment she creates two outcomes, all Bell-type argument and all your argument do not work. So there is no proof of action at a distance when Alice creates two outcomes. You can still have complete correlation. She creates two outcomes, and one of her outcomes made complete correlation to another outcome, which is this non-locality of words, entanglement. But there is no any action at a distance. So if you want to, if the non-locality is action at a distance, you don't have a proof. And many word is a counterexample into this story.
Okay. Okay. I mean, the problem, I have so many objections to many words that if we go into that, we'll spend the rest of the evening.
No, I'm planning to, I probably, if it's okay, it's interesting, I will spend things about, I will give at least one talk about many words, maybe something about, another talk about local theory of the Deutschenheit.
But maybe Tim can explain more why many words not local. To me, since there is no space-time, really, I don't see how the issue of locality can even be raised. But
can I
well, there is, I will explain. In my many words, the space-time is crucial. This is part of the story. We live in 3 dimensions, so causality in 3 dimensions. I have to do everything is local. I have to take this cup in 3 dimensions. So, and the wave function of macroscopic objects for whom we have to explain, they all local in 3 dimensions. So it's not the wave function reality of Dave Albert, who trying to say, let's look on this configuration space and bite the bullet and trying to say that this is a story. No, the part of the many words is 3 dimensions, that interactions are local and macroscopic objects live in 3 dimensions. The words, in every wave function of a word, the wave function of macroscopic object is 3-dimensional. It's not entangled with anything. So then we have a causal, normal, local story inside the word.
Yeah.
Tim, there was a finger, I think.
Yeah, Tim, go ahead.
I mean, maybe it'll help to clear up a little of this terminology. Ironically, to make it a little more complex. So we've got Bohm, we've got many worlds, we have collapse theories like GRW, right? There's a way of defining action at a distance that GRW would agree with Lev and say, oh, this theory has no action at a distance, but it's non-local. I mean, just listen to what Lev said. Lev said, he admits that many worlds is non-local, but he wants to make a distinction between being non-local in one way and in a stronger way, which is what he calls action at a distance. Yeah.
Yes.
Let's not worry about that distinction. It's associated with the distinction between parameter and outcome independence, that old distinction. But Lev says it's non-local, so we have no dispute that it's a non-local theory, right? Where Lev thinks that action at a distance is even more objectionable, right? He doesn't want that, but he accepts the non-locality. You can argue that there's no action at a distance in GRW. That's a single world theory. So it's not.
Of course, there is action at a distance in GRW.
I'm saying you can argue, it depends on how you define.
No, it's not true. There is action at a distance in GRW. You can change, you can make a measurement or not make a measurement. This will collapse, this will create, if you have an entangled system, it will create collapse on other parts. GRW is action at a distance.
I exactly didn't want to get into a precise definition of action at a distance because people will disagree about what some people associate it with signaling. Okay, it's just that's a terminological mess, right? I hope what we agree is that the only assumptions of Bell are locality and statistical independence.
And single word. And single word. Without single word, there is no Bell.
Okay, but then
all this Bell doesn't. His algorithm doesn't trace.
Okay, but you're not going to say the many worlds avoids the non-locality because you agree there is non-locality.
It avoids action at a distance.
Okay, but not non-locality, and as I said, Bell's assumption.
What does it mean? What does non-locality means if there is no action at a distance? That's not clear to me.
Well, because without action at a distance, if you have complete description of all local facts, you have local information everywhere. You take some of all this information. This is not enough to explain nature. So therefore, quantum mechanics is non-local. Because you cannot explain EPR, if you have two pair of EPR, you have complete description of one particle, it's a density matrix, completely unpolarized electron, another completely unpolarized electron. But there is some relative phase which is important, and it's not in a local description. You cannot attach it not to one and not to another one. Therefore, quantum mechanics, EPR, wave function is non-local. But you cannot come to one electron, do something to it, and change local description of another one. Another one is density unpolarized electron. When I measure mine, the other one still unpolarized electron if I look on all nature together, all worlds together. So I cannot change whatsoever far away.
Yeah, but what I would challenge then is the question of how do you explain the perfect correlation? You see, that's
because it's non-local. There is kind of foliation, and this word connected to this word in non-local way. This non-locality exists. There is this non-local connection exists. Non-local action doesn't exist. And Newton and Einstein were against action at a distance. They were not less about this non-local connection. I don't think that they express a serious feeling. This is the correlation, stronger correlation, whatever, even non-local correlation at one thing. Action at a distance, this is what's unthinkable. Because if action at a distance exists, why were local objects? There is no reason for us. Then we can think about kind of creatures which are non-local, and if there is this possibility to act far away, then all the fact that all object, all conscious being, everything are local is unexplainable. And the fact that everything, this is why action at the distance is so strange.
Lev, you know that Bohmian mechanics is a counterexample to the sketch of an argument you just tried to give.
What do you mean? Bohm is non-local. It's non-local. I can change. I cannot, if I do something here, I don't change anything there immediately, but later the velocity will change, so it will cause a change. So I can change almost immediately. It's non-local theory.
Right, but it perfectly well explains why you have what appears to be a local world until you look at it too closely. It explains why evolution can't take advantage of non-locality.
No, but the fact that, you know, it's like when I discuss it with Aronov all the time. He likes non-locality.
Who?
Yakir Aronov, my teacher,
Oh, yeah.
my collaborator. He likes very much non-locality. He has this modular variables which explain nice. He has Aronov-Bohm effect. He has all kind of non-local things. And I think I don't say that they don't bring interesting phenomena. But all what he shows that if you have a non-local concept, it has non-local equations. So now in case of Bohm, it's a different story because the only way not to have action at a distance to have parallel worlds. And if you hate it, and Bohm apparently hated it, or really it's not Bohm. Bohm didn't care about this. So if you want single words, then you have to do this non-local story. No way, there is no way out. Like this Bell theory about whatever John Stokes says, if you want a single word, you must have action at a distance. No way out.
I still don't understand why there's no action at a distance of many worlds because I don't understand many worlds really. But anyway, maybe Tim has a comment about that.
I'll just say this, but I don't want to get too bogged down. If you take the GRW flash theory, okay, so the local beables are these flashes, you will not have, in your sense, action at a distance.
But I think
it's just a fact. I'm just
no. Just I want to comment on the fact because even also in Bohm, for example, in Bohm you say, well, what is reality in Bohm? Some people, I don't know, Shelley was in a direction trying to say that it's a law, that the wave function. But for me, the wave function is part of the reality. So if you can change, now in Bohm, you don't change the wave function far away. But I think GRW, the wave function is very important. So I can change the wave function far away. Therefore, it's non-local. For flashes, I can make some exercises and to make it look relativistic, but it's not. No, it's not of. I think even Tomulka himself doesn't consider it very serious. So every collapse theory is action at a distance. Even if you add flashes, which I think no one needs. The original GRW, it's beautiful and you don't need anything else.
No, you need an ontology. But anyway, let me say
wave function ontology. GRW, single word.
No, because I don't agree. Okay, that's what we don't agree.
Also because, Lev, I wouldn't spoil all your talk since you want to, it would be a shame. So thank you first for accepting the invitation live here today. So that's nice.
Let me say something to
yes.
things which I don't understand. If you take the Einstein box experiment and you describe it in terms of GRW with flashes, it seems to me that you are, by opening one box, you are creating flashes on the other boxes. That's more non-local even than Bohm, because it's non-local even for one particle, which Bohm is not.
There'd only be one flash. It would be in one box or the other.
No, because you detect the particles, there'd be many flashes.
We would need to exposit the flash theory for this discussion to be comprehensible. So we shouldn't get into the details, I think.
If I may, since we have 3 minutes and maybe two small questions, may I ask if, since I see that one of the ways to further develop the discussion might be to understand whether this locality entails action at a distance necessarily, or it entails something else. This seems to be something that interests both you and Lev and also GRW. So I don't know if for next week, Tim, if you will be around. I don't know. So well, anyway, so let's put it that way. Anyway,
I think
let's try to see if you can, it would be nice if you can sort of give a very short explanation of why outcome and parameter independence is a spurious distinction, and maybe say something about the Jarrett and Shimony, and also I forgot about the third one. Well, so non-separability. That would be something that maybe helps us to get somewhere in the discussion, because also I would be interested in hearing that. If you can come, we'll discuss about that anyway.
But what time? What time? Where, because it's usually scheduled from 2 to 4, so you want to do it 4 to 6?
If Tim can join, which again, I'm not forcing you, of course we will do the same time, or maybe, I don't know.
That would be, I mean, I could get up that early, but.
No, we won't do 2 p.m. We won't do 2, we will do either like today or, I don't know, we will adjust. But anyway, let's discuss about that this week. Okay. And so, made for the same reason, I would suggest that the 2 questions that are on hold wait next week, because we are all tired, I guess.
Yeah, a little bit, yeah.
So that we don't have to rush on things. So I'm sorry to Giuliano, and I'm sorry to Jeremy. And yeah, that's it. You can go back to watch CNN. And thank you, John. Thank you, Tim, a lot. And see you next week.
Okay, see you.
Bye, guys.
Thank you.